In the beginning, God said, "Let there be light." And there was just what exactly? What is light? How does it differ from darkness? Some early Greek scientists thought the eye itself was the source of light. They believed that light was a kind of streamer. These light streamers were emitted from the eye. Without the eye, there could be no light. Others believe light came not from the eye, but from different sources. But whatever the source, it seemed reasonable to believe that light traveled from one place to another. Attempts were made to measure the time it took for light to travel or propagate. Unfortunately, scientists could not observe the propagation of light. In some mysterious way, light appeared everywhere, instantaneously. This was beyond human understanding until the invention of the telescope. In the late 17th century, Olaf Romer studied light from Jupiter at several points on the Earth's orbit. His observations could only be explained by assuming light traveled across the Earth's orbit in about 16 minutes. That's a distance of more than 300 million kilometers. At last, here was evidence of the enormous speed of light. Scientists had long searched the familiar world around them for models to help explain propagation of light. Not long after Romer's observations, the respected scientist Sir Isaac Newton lent his weight to a particle model of light. His particle model was the first to explain several important behaviors of light. Newton made carefully reasoned assumptions about things he could not observe. He knew that when a stream of actual particles intersects with another, there are always collisions. These collisions cause particles to spread out from the intersection. But when two beams of light intersect, there's no evidence that light particles collide and spread. So Newton assumed that the light particles must be incredibly small, too small to ever collide with each other. Newton also made an assumption about particle motion. He knew from observations that moving particles are pulled by gravity to follow a curved path. The faster the particle, the straighter the motion. So Newton assumed a particle moving as fast as light would show straight line motion or rectilinear propagation. This assumption about particles matches experiments with light and shadow. These experiments show that light tends to travel in straight lines. Particle behavior can explain several well-known properties of light. traveling particles tend to bounce off a barrier. The angle at which a particle strikes the barrier matches the angle at which it leaves the barrier. This geometry of reflection can be demonstrated with many particles. And at many angles. This particle behavior is a good model for light, because a beam of light reflects from a mirror in the same way. Another behavior of light is refraction. Newton knew that transparent substances, like water and glass, distort light. It seems as if light bends as it enters a new medium. But why? Newton proposed that all particles of matter exert an attraction on every moving particle of light. This attraction is balanced in all directions, so light normally travels in a straight line, except near the edge of another substance, such as water. A light particle approaching the surface of water encounters a stronger force of attraction. This causes the light particle to bend towards the surface and speed up. Once inside the new medium, the greater force of attraction pulls evenly from all sides, so the light particle continues in a straight path. However, Newton had no way of showing that light actually travels faster in water. It was one more assumption necessary to his particle model. Yet another behavior of light is dispersion. Newton had himself discovered this property of light. He shone light through a slit to produce a narrow beam. With a prism, he interrupted the beam. The prism split white light into bands of color. To explain this behavior, Newton suggested that a beam of light is a mixture of particles of different sizes. The surface of the glass attracts them, and they bend according to their size. So the prism separates light into streams of same-sized particles. These streams appear as different colors to the eye. Just how solid was Newton's particle model? Newton himself was cautious about it, but his famous name was enough to sell the scientific community. In spite of attacks, especially from another important model, Newton's model survived and was accepted for nearly 2 centuries. What is light? Why does it behave the way it does? Over the centuries, scientists chose models from the world around them to explain light. The particle was the first widely accepted model for light, thanks to Sir Isaac Newton, who first formulated a particle theory to explain several behaviors of light. But there were a few scientists who favored another model for light, the wave. Waves are a traveling disturbance, which transmit energy from one place to another. In the 17th century, all known waves required a medium, such as water. So it was proposed that air, and the space around us, is filled with an invisible medium called ether, in which light waves propagate. About the time Newton was developing his particle theory, another scientist, Christian Huygens, proposed a detailed wave model of light. This wave model more easily explains some behaviors of light. Diffraction, for example. If a tiny slit is made and light shone through it, the edges of the pattern are not sharp. Huygens compared this behavior to diffraction of water waves. If waves are interrupted by a barrier and a gap is made, only part of each wavefront propagates through the barrier. As the wave passes through the gap, it bends around to either side. Huygens proposed that in the same way, light bends around the edges of a slit. This produces a fuzzy edge created by bands of dark and light lines. Huygens used waves to explain several other behaviors of light, including geometric reflection. When a mirror reflects a light beam, the angle of incidence always equals the angle of reflection. Water waves behave the same way, although their behavior can appear confusing. Note the direction of propagation to the wall and away from it. The angle of incidence is equal to the angle of reflection. Huygens also used water waves to explain refraction. When waves move from deep water into shallow water, they change direction and slow down. The result is a change in the direction of wave propagation towards the normal. In much the same way, a beam of light changes direction as it passes from air into water or glass. Huygens reasoned that if light is a wave, since it bends towards the normal, it must move slower in the new medium. His prediction contradicted Newton, who felt light particles, attracted by the pull of the surface, must move faster in water. Huygens' explanation of these and other behaviors of light were just as convincing as Newton's, but Huygens lacked Newton's reputation. Largely for this reason, his wave model of light was neglected for more than 100 years. But slowly, evidence began to mount in favor of the wave model. A major breakthrough came in 1802, when Thomas Young confirmed the existence of light interference. Interference had been considered a weakness of the wave model of light. When two sets of waves intersect, a characteristic pattern of peaks and troughs is created. Critics of the wave model pointed out that this interference cannot be seen when two beams of light intersect. But Young proved them wrong by using a pair of tiny pinholes very close to each other. His experiment also works with two narrow slits and is a little easier to visualize. If light is shone through these slits and projected onto a screen, a pattern of light and dark lines can be seen. This interference pattern can be explained by using water waves. If a barrier interrupts the waves, any slit in the barrier acts as a point source of the waves. Two slits create an interference pattern. The intersecting crests of the waves migrate outward along fixed lines. At each crest intersection, the two waves interact. They reinforce each other to increase the amplitude of the wave. This is called constructive interference. Constructive interference also occurs when two troughs meet. When crest meets trough, destructive interference occurs. The waves cancel each other out and create a dead spot in the wave pattern. And so two slits produce lines of high amplitude caused by constructive interference. And between them, lines of zero amplitude caused by destructive interference. This wave interference pattern nicely explains the light pattern created in experiments like Young's. In 1850, there was yet another boost for the wave model. In that year, Jean Foucault successfully measured the speed of light in water and found it to be slower than in air. This destroyed Newton's particle explanation, which required light to move faster in water, and confirmed the wave model prediction that light moves slower in water. These experiments and others gradually eroded support for the particle model. By the mid-19th century, the wave model of light was triumphant. What exactly is light? Throughout the 18th century, most scientists preferred to model the behavior of light with a particle. Sir Isaac Newton made the model popular, and for years his personal fame protected it from attack. But by the early 19th century, the particle model had been eroded and replaced by the wave model of light behavior. which was first proposed many years previously by Christian Huygens. The wave model explained many behaviors of light, but it was far from perfect. For example, no one had been able to prove the existence of the mysterious invisible ether, the medium which filled the air and space around us and was apparently necessary to convey light waves. In the mid-19th century, a remarkable scientific mind added a new twist to the wave model. James Maxwell was a theoretical physicist. He worked principally with mathematics. Maxwell made a brilliantly conceived prediction. Light is a wave, formed by two of the fundamental forces of nature, electricity and magnetism. Just what knowledge did Maxwell have to work with? It was known that when electricity flows through a wire, it creates a magnetic field around the wire. When the rate of flow changes, the strength of the magnetic field changes too. Maxwell was also aware of a closely related phenomenon. If a magnetic field changes in strength, an electric field is produced. This will cause a charge to flow through the conductor. Could a single particle carrying an electric charge have similar fields associated with it? Maxwell theorized that when a single charged particle moves, it creates a magnetic field. If it changes speed, the strength of the magnetic field will also change. Could this changing magnetic field in turn induce a changing electric field, in turn producing a change in the magnetic field, and on and on? Maxwell constructed a mathematical model to make one of the most important predictions in the history of physics. His calculations predicted that if a particle which generates an electric field is accelerating or oscillating, it creates a changing electric field, which propagates away from the charge its strength changing in the form of a wave. At right angles to this changing electric field is a changing magnetic field, also propagating as a wave. These fields need no medium, such as ether, to convey them. Just as a magnet, for example, works in any medium. And just as the electrical force between two charged particles acts, even in a vacuum. Maxwell's calculations showed that these electromagnetic waves can reinforce each other endlessly, but only if they propagate at one particular speed, a little more than 300,000 kilometers per second. And that just happens to be the speed scientists had calculated for light. Is light a form of electromagnetic radiation? A fascinating possibility. But there was no evidence that electromagnetic waves really existed until another giant of physics tackled the problem. Heinrich Hertz set out deliberately to find physical evidence of Maxwell's electromagnetic waves. He built an apparatus using a transformer to increase voltage and produce a spark between two terminals. This spark caused a charge to oscillate backwards and forwards between two plates attached to the terminals. Is this device a transmitter of electromagnetic waves? If so, how to detect the waves? Hertz tried many devices, including a single wire loop with a small gap in it. Hertz placed this antenna near his transmitter and was able to observe tiny sparks jumping the gap in the antenna. Clear evidence that the loop had absorbed some of the energy emitted by the transmitter. This work confirmed Maxwell's prediction that electromagnetic waves result from accelerated charges. Scientists have since discovered an infinite range of different electromagnetic waves. Because they all travel at the constant speed of light, they can be identified either by the length of a single complete wave or by the number of waves that pass a point in a second, expressed as cycles per second or hertz. The wavelengths, which Hertz used in his experiments, are today called radio waves. On a scale of wavelength, radio waves range from many kilometers in length down to a few centimeters. Shorter than radio waves are microwaves, ranging down to wavelengths of a few millimeters. Still shorter are the infrared waves. We feel these as radiant heat. The electromagnetic radiation we actually see, visible light, is an extremely narrow band of wavelengths, only 2 times 10 to the minus 7 meters wide. Shorter than visible light waves are ultraviolet rays. Shorter still, X-rays. And on down into an endless sea of incredibly short gamma and cosmic radiation. Over the last century, we've discovered or created transmitters to produce a vast range of this radiation. Light itself is transmitted from accelerated charges within atoms. Maxwell's electromagnetic wave model was so useful that for nearly a century it seemed the final explanation for the behavior of light. What is light? How does it differ from darkness? By the late 19th century, light was known to be a form of energy, transmitted or radiated, emitted from one group of atoms, and often absorbed by another. Scientists developed a useful model of this radiation, the electromagnetic wave. Light behaves as an electric wave, interacting with a magnetic wave, propagating through space at over 300,000 kilometers per second. This wave model explains most, but not all, behaviors of light and other forms of radiant energy. At the turn of the 20th century, a German physicist tackled one of these unexplainable behaviors. His name was Max Planck. and he was interested in the way energy was shared by atoms and the space between them. Electromagnetic theory could not predict the results, which were observed by using a closed box, in which radiation bounced back and forth. But Planck found a way to mathematically predict the actual observations of energy distribution. He proposed that atoms are restricted in the way they radiate energy, and that each atom can only emit discrete, measurable bundles of energy. Planck called such a bundle a quantum. He proposed that the energy of each quantum emitted is determined by the frequency of the radiation. In other words, it is equal to the frequency times a constant. Planck roughly calculated this constant, and he used it to predict energy emissions by atoms. This quantum idea revolutionized physics when another brilliant physicist, Albert Einstein, carried Planck's ideas a step further. He applied the quantum idea to what is known as the photoelectric effect. This effect can be studied by sealing two metal plates in a vacuum and connecting them to a battery, which induces an electric charge on each plate. If the negatively charged plate is coated with potassium, then illuminated with blue light, electrons are emitted from the negative plate and attracted to the positive plate. But if red light is used, no electron flow occurs. Before Einstein, scientists tried to explain and predict this relationship between light and electric current using the electromagnetic wave model. Their prediction? When electromagnetic waves strike atoms, energy is transmitted to the electrons. Some of the electrons escape from the atoms. Since red light did not cause emission of electrons, it should only be necessary to increase the intensity of the red light to transfer more energy to electrons and produce emission. That's the prediction. In fact, it fails to happen, no matter how bright the red light is made. But any radiation with a frequency equal to or greater than blue light does cause emission, even if the light is faint. What's more, the wave model also predicts that more intense light at these frequencies will transfer extra energy to the electrons. In fact, it does not. Increased intensity simply makes more electrons flow. These observations just can't be explained with a wave model. So Einstein used Planck's quantum idea instead. He proposed that atoms cannot simply absorb any amount of radiation. They can absorb only discrete bundles or quanta of radiation. This can cause atoms to emit electrons. But why the difference between blue and red light? Planck had already proposed that for emitted energy, the energy of a photon is proportional to the frequency. So a higher frequency means more energy. Einstein proposed that the same reasoning could be applied to absorbed energy. Red light shining on a potassium-coated electrode produces no emission because individual photons of red light do not have enough energy to liberate an electron from a potassium atom. But blue light photons do have enough energy to liberate potassium electrons. The quantum prediction. Even higher frequency photons have more than enough energy to produce emission. The excess energy transfers to the electrons. And that's just what happens. What's more, the quantum idea predicts that if the intensity of light is increased, it means greater numbers of energy bundles. More bundles means more atoms can absorb energy and release more electrons. So the quantum idea predicts an increase in electron flow. This prediction, too, matches what happens. So we have evidence that energy is emitted from Planck's atom in a quantum and absorbed by Einstein's atom in a quantum. It seems logical to assume that electromagnetic radiation is comprised of bundles. Einstein called these bundles photons. But the photon hands us a new problem. What exactly is a bundle of waves? Waves are continuous and are described by their wavelength. A bundle is a concept better described not by a wave, but by a particle. Thanks to Planck and Einstein, the particle model of light, long discredited, was rediscovered. The wave model was still essential to understanding. Light and other electromagnetic radiation seem to require not one or the other, but both models. With this discovery, the modern era of quantum physics was born. What is light? Why does it behave as it does? The early struggle to explain light was a war between two models. Sir Isaac Newton's particle model battled Christian Huygens' wave model. As time went by, evidence mounted in favor of the wave model. It was improved and became Maxwell's electromagnetic wave model. It looked like the end for the particle. And then, to the surprise of the entire scientific community, Max Planck, Albert Einstein, and their quantum model gave new life to the particle. The light photon is a powerful new way of looking at an old idea. It helps to explain long-predicted behaviors of light, like pressure. real particles exert pressure. Newton himself formulated laws of momentum. Which helped to explain pressure. The product of a mass and its velocity is known as momentum. If a stationary mass is struck by a moving mass, the momentum is transferred. If we add up the momentum of two masses before a collision, and after, the momentum vectors after the collision always add up to those before the collision. In 1923, scientist Arthur Compton showed that photons also appear to have momentum. He used a cloud chamber in which tracks left by atomic particles can be observed. He fired X-rays of known photon energy into the chamber. Occasionally, the stream of X-rays produced the track of an electron. At the same time, Compton discovered that X-rays had been deflected at an angle. The photon energy of these X-rays was reduced. Compton showed that this collision is similar to a collision between two particles, in which momentum is conserved. He calculated from the photon energy that if a photon has momentum, when it interacts with an electron, the momentum is conserved. Compton's demonstration was evidence of the particle-like nature of light. Conservation of photon momentum supports the prediction that light exerts pressure. We can actually see the results of this pressure in the heavens. Scientists generally accept that the photon pressure pushes the tiny particles that form the tail of a comet, so that they always stream away from the sun. Some visionaries have proposed that gigantic sails could catch this photon wind to push spaceships between the stars. And what about other behaviors of light? Can scientists use the photon particle to explain them all? Interference patterns, for example. The wave model nicely explains how constructive interference produces lines of brighter illumination to create distinctive interference patterns of light. Can particles describe the same pattern? Imagine that light is composed of many photon particles instead of waves. Could it be that these particles interact in some yet-to-be-discovered way to produce the interference pattern? Jeffrey Taylor provided a dramatic answer to this question. He set up an experiment which used photographic paper to record interference patterns. This light-sensitive paper gradually records a pattern even if the light is weak. Taylor repeated the experiment, reducing the level of light entering the slits until it took months to produce the pattern, to the point where he calculated that on average only one photon at a time approached the slits. And what was his result? How could the same pattern be explained by particle interaction. With only one photon in the apparatus at a time, no interaction was possible. In spite of the quantum theory and the photon model, we still need the wave model of light to predict just where the photons will strike after passing through a slit. Taylor demonstrated that the particle model cannot provide all the answers. The wave model is still an essential tool for describing the behavior of light. Is one model more useful than the other? That depends at least partly on the kind of electromagnetic radiation. Some forms of electromagnetic radiation are more wave-like. Radio waves, for example, with very long wavelengths, clearly demonstrate wave characteristics, like interference. For example, a radio wave in its reflection can set up an interference pattern. On a car radio, we can often hear this as peaks of intensity and dead spots as we move across the pattern. But it's difficult to detect a single photon of radio radiation. At the other end of the radiation scale is gamma radiation. These wavelengths are so short that it's difficult or impossible to demonstrate interference with slits, no matter how tiny they are. On the other hand, the energy travels in particle-like photons, which are easy to detect as separate clicks of a Geiger counter. Quantum physics and the photon model of energy radiation have changed the face of modern physics. And yet, the electromagnetic wave model is still an essential tool. Today, the two models support each other to provide us with a clear understanding of light. What exactly is light? Today, scientists need two models to explain light and other forms of electromagnetic radiation. Waves and particles. We model radio emissions with waves because they clearly demonstrate wave characteristics, like interference. On the other hand, gamma radiation shows few wave characteristics, but single gamma photons can be detected with a Geiger counter. Sometimes, both models are necessary. For example, single photons of light passing through a pair of slits will eventually produce a characteristic interference pattern. But what path does each single photon follow? The probability is high that any single photon will strike one of these bright lines. To actually calculate the shape of this probability pattern, we need to use the wavelength of the radiation. Some scientists like to think of the wave as a property of the photon particle, which is useful in determining its probable path. Strange that one model, the particle, somehow depends on another, the wave, to explain the behavior of radiation. So strange, in fact, that a university student made a daring prediction. Louis de Broglie suggested that actual particles, a piece of dust, or an apple, can behave like waves. The implications of his idea seem ridiculous. Consider that day in Mudville when mighty Casey struck out. But did Casey really strike out? Or did de Broglie? Actual particles, no matter how small, sometimes collide. If the bat and the ball are particle-like, they are capable of connecting. But waves can pass right through each other. If ball and bat are wave-like, they might be able to pass right through each other too. So was it really Casey's fault, after all? Well, de Broglie developed an equation that linked the wavelength of a particle to its mass and velocity. This de Broglie wavelength can be used to determine if an object's behavior will be particle-like or wave-like. Let's look at the implications. Consider the bat as an obstacle and the ball as an approaching wave. Wave experiments show that if the wavelength is much larger than the obstacle, the waves diffract around it easily. Our wave ball bends around the bat and carries on unchanged. But if the wavelength is much smaller than the obstacle, less diffraction occurs and a shadow region appears behind the obstacle. Our wave ball cannot bend around the bat. So, is the de Broglie wavelength of a fastball large or small? Small. So small that the ball cannot diffract around the bat if it's heading directly for it. The two collide just as we expect.
You're out!
Or at least they should collide if Casey has his bat in the right place. To make the wavelength larger, we either need to make the mass smaller or the velocity smaller. What kind of particle might have a de Broglie wavelength that is large enough to observe wave effects like diffraction and interference? Consider one of the smallest particles, an electron. What might its de Broglie wavelength be? If its mass is 9.1 times 10 to the minus 31 kilograms. And it travels at 3 times 10 to the 6th meters per second. Although this wavelength seems small, it's no smaller than that of an X-ray. We can demonstrate the wave nature of X-rays by using, of all things, a crystal of salt. The atoms of the crystal line up to produce a series of slits running in 2 directions. X-rays passing through the salt crystal produce this interference pattern. Could electrons show evidence of their wave nature in the same way? The answer is yes, Electron particles passing through a crystal produce a very similar interference pattern. An electron is a particle of matter, yet it has wave characteristics, just as the photon has wave characteristics. Then, is there any difference between an electron particle and an X-ray photon? There are several important differences. One of the most obvious is speed. To have a de Broglie wavelength similar to that of an X-ray photon, the electron must travel about 3.6 times 10 to the 6th meters per second. By contrast, in a vacuum, the speed of an X-ray photon is almost 100 times as great, 3 times 10 to the 8th meters per second. Another important difference is their rest mass. The electron has a rest mass of 9.1 times 10 to the minus 31 kilograms. When a photon is stopped, it is annihilated. Light is like a particle, but it's not a particle. Although de Broglie has shown us that particles and waves are themselves related, when it comes to electromagnetic radiation, the models remain just that, models. We know that light is like a particle and light is like a wave.